Remember, mixtures are when you have things physically combined. A true solution is when you have really small molecules. They don't separate out. So that's like sugar in water, salt in water. Colloids, on the other hand, is where the molecules are bigger. So I would say they're kind of medium-sized, but they do stay mixed, so they do dissolve in the solvent. They tend to make that mixture thick, right? So we said like gravy, Jell-O, egg whites. Those were all examples. Cream, that have large molecules that stay mixed. Then you've got suspensions. Suspensions were where we quit last time. So suspensions are when you have really big particles. They don't dissolve, but they can get mixed or shaken into the mixture. But if you stop shaking it, if it's allowed to stand, then it's going to separate out. So we said blood is a suspension. Blood cells, if you let a sample of blood just sit without any kind of chemical to keep it soluble, like heparin, to keep it from clotting, it will clot and it'll separate out. You can also take a sample of blood and centrifuge it. Things that are heavy go down to the bottom. Things that are light stay on top. Plasma is less dense than the blood cells, so that's why the bottom becomes dark in color with red blood cells. The top becomes kind of straw-like yellow liquid because that's the plasma, the fluid part of the blood. So then we went here. And so it's just kind of reiterating that blood is a suspension because red blood cells, white blood cells, and platelets, they are suspended in the blood. They stay mixed because blood is always moving. The colloid part of blood is in plasma. So plasma has proteins, 3 basic types. There's albumins, immunoglobulins, and then clotting proteins. So those are the 3 kinds of proteins that you find in the blood. Albumins help to keep a water balance. Immunoglobulins, those are antibodies. And then clotting proteins, they help to clot the blood if a blood vessel gets damaged. But those are all big molecules. Okay, they're big, they thicken plasma, they kind of give plasma this sort of like thick texture, and that's because of these. But the true solution, you can really say blood is a true solution as well, because there's a lot of solutes that are very small, dissolved in blood, and don't separate out no matter what. So if we have very small solutes, most of these are dissolved in plasma. And these are going to include things like nutrients, right? Like blood sugar. So when they talk about your blood sugar, they're talking about this sugar dissolved in the blood. If you're talking about salts, like sodium, chloride ions, those are dissolved in the blood. They don't separate out. So even if the blood stands and separates, these things are still going to be dissolved. Waste molecules, these get filtered out in the kidneys. So these are things like urea, uric acid, creatinine. So these very small solutes stay dissolved in the blood, even if the blood itself clots or if the blood itself stops moving, because that's the component that's really a true solution. So the blood has really got all of the different characteristics of a solution. It's true solution, colloid, and suspension characteristics just because of the things that are mixed into it. Okay, so when you're talking about a true solution, so just think about salt and water. True solutions, they can have a little bit of solute or a lot. So oftentimes it is variable solute. So this is the example I said, like if you have coffee, some people like 1 teaspoon of coffee in their or 1 teaspoon of sugar in their coffee. Some people like 2, some people like 3, some people like fill half of the jar, half of the cup with sugar and then pour in coffee and get it to dissolve. So that sugar is the solute. And you can change how much you add in to give a variable sweetness. So if you put as much sugar in your coffee as possible, you can't dissolve any more, then they would say that that is a saturated solution of sugar. Just think saturated means it has as much as it can possibly hold. And they do show you kind of like a picture. Something that is unsaturated, you can add more sugar to. So if you have 1 teaspoon of sugar in your cup, that's an unsaturated solution. You can add another spoonful, stir it up. It totally dissolves. You can add another spoonful, stir it up, totally dissolves. But if you get to the point of what they call a saturated solution, you have the maximum amount of solute dissolved. And so if you look, there's going to be solid solute in the beaker. Bless you. So this is the maximum solute that can dissolve is a saturated solution. So you can have that with lots of different solutes, like honey is a saturated solution of sugar. If you were in lab, we made soap, and one of the last things that we added was a cold saturated solution of sodium chloride. So it had as much sodium chloride dissolved as it possibly could. And remember, the bottle had some solid down in the bottom. So when you sort of like mixed it back and forth, you could see some white crystalline salt still in the bottom that didn't dissolve. That's a saturated solution. Whereas just remember, unsaturated means I can add more. Okay? I can add more solute if it's unsaturated. Gout, kidney stones, those are examples of what happens when solutes become saturated in certain compartments in the body. So with gout, it is a waste molecule called uric acid. So uric acid is normally filtered out by your kidneys, but in some people, the uric acid builds up in the joints. So it starts off, and there's a little uric acid in that synovial fluid. That's okay. It stays dissolved. But then more uric acid is added to that joint capsule, and then more, and then more. And eventually it gets to the point where it's saturation. There is as much uric acid in that synovial joint. So these are your movable joints. Like actually where the synovial fluid is, uric acid, it builds up and builds up and builds up, and eventually it forms crystals. So it actually forms, much like salt crystals, the uric acid forms crystals between the bones, and then when you move that joint, how does that feel? Have you ever taken care of a patient with gout or seen somebody that has gout in a joint? Usually that joint will get really inflamed and even look bruised. It'll look like red, black, and blue, almost like somebody hit it. And that, yep, so it's uric acid crystals that collects, and eventually, well, uric acid collects in the joint, and eventually it gets to a point where it's saturated, and once you add any more, now it's going to crystallize. So it actually forms crystals in that joint capsule. And so any kind of movement is painful. It feels, people say it feels like there's like little, like sharp, pointy crystals in the joint. So that causes pain, inflammation, loss of mobility. Some of that is diet related. Kidney stones are another one. So kidney stones can have uric acid like gout does, but it can also have calcium salts. It can also have some like calcium phosphate, calcium oxalate. Normally your kidneys filter this out, but in some people, there is so much waste as it passes through the kidney, that waste molecule concentration builds up to the point that it reaches saturation. And once it becomes saturated, now you've got this. Now you got this solid that begins to form. So you see like in the bottom of that beaker, that white solid. So that ends up being your kidney stone. So it starts, and once one little crystal forms, the other little crystals will start sticking to it. So that's why they call it a stone, is because oftentimes it forms sort of a round shape, and it's some type of salt that got to the point that it was saturated. Any more of that salt added to the solution causes that crystallization. So sometimes it can form in the kidney itself. and actually block filtration. It can form right as the fluid leaves the kidney, like in what they call the renal pelvis. And so then the renal pelvis is like a funnel. So you get stones that then drop into this funnel that goes like this. So what's going to happen? That stone's going to get stuck like at that narrow spot. Sometimes the stones get stuck in the ureters. The ureters are the tubes that carry urine from the kidneys to the bladder. If they get into the bladder, usually it's not as bad to pass them, just because the bladder and the urethra are a little bit bigger in terms of tube. The most painful that I've heard is when they're in the kidneys and you're trying to pass them, move them from the kidneys down the ureter and into the bladder, because those are really, really small tubes. And so any kind of crystal in there causes a lot of pain. So both of these, they can give you medication to try and decrease this solubility, but you've also got to drink a lot more water. You've also got to avoid food that is causing these crystals to form. So if you make kidney stones that are mostly calcium, then they really want you to limit your calcium intake, because there's too much calcium getting flushed in the kidneys, so too much calcium is building up. Uric acid, like having like pork, fried foods, some of the like it's not so much your green vegetables, but it's green vegetables that you end up putting like meat drippings on. So it's like collards, and then you like fat back like on them, or you have a lot of people like keep their like roast drippings and such, and then use that as their seasoning, but that can end up creating a lot of uric acid. So sometimes it's diet, sometimes it's medication that has to be used, because worst case scenario, this can stop kidney filtration. It can actually cause one of your kidneys to shut down, because it could cause like literally like a plug and stop urine from being able to pass by. So it would like plug the kidney, and then the kidney can't do filtration anymore and it shuts down.
We can have dialysis.
And then you might end up having to have dialysis because of it. So kidney stones can lead to that. Gout really is just super painful and decreases mobility. Like you can barely walk on a joint that's got gout in it.
I heard that I have a friend that lives down here in Indian. He said he got gout from eating things like hot dogs, bologna.
So a lot of that's all pork. Like those are all those pork products. So pork is one that is kind of got like the bad rap, whether or not it's pork that's like preserved, like it's bologna, which has a lot of nitrates in it. So it's those molecules, like the waste molecules from their breakdown. So limiting the amount of pork and pork sort of fat that you're ingesting. Well, because it creates more uric acid, which then leads to crystals forming in the joint, which is what gout is. So, yeah. But now some people have no problems with it. Some people never have gout and they eat pork all the time. So it really depends on your metabolism, how your body gets rid of it does have a play. But this is an example of where saturation can end up causing a problem. If you have more solute than can stay dissolved, it's going to end up forming a crystal. So we're going to talk about those later. I'm just going to skip them. So this is talking about, well, when a true solution is formed, those solutes dissolve. When they dissolve, some of the solutes are electrolytes, and some of them are not. So electrolyte, the term electrolyte was made because it sounds like electricity. An electrolyte is a solute that can form a charge. So one that sodium chloride. So if you put sodium chloride, if you take salt crystals and you put them in water, they 100% form sodium ions and chloride ions. Right? So in this one, NaCl, it's a solid, like your table salt. You put it in water, stir it up, completely dissolves. When it dissolves, it forms sodium ions and chloride ions, and it does this 100%. Okay, so none of the sodium chloride remains together. It all dissolves. And we're talking about not a saturated solution, just an unsaturated solution.
Is that AQ?
AQ means what? That stands for, S would be solid, and AQ is, when it's dissolved in water, it's aqueous, right? Remember, AQ means that it's aqueous. So those little points that are in the parentheses are just telling you the form that that salt takes. So because this dissociates 100%, they call this a strong electrolyte because you make lots of ions. The example down here of magnesium and chlorine, magnesium chloride, when it dissolves, it forms 100% magnesium and chloride ions. And so notice there's lots of ions. Those ions can carry an electric current. So that is where the name strong electrolyte came from. A strong electrolyte forms 100% ions when you put it in water. And a lot of ionic compounds have that characteristics. So 100% charged ions are formed. But then sugar. Sugar is not an ionic compound. Sugar is a covalent compound, but it does dissolve in water. So if it's a covalent compound that can dissolve in water because it's polar, because it has lots of those OH groups, they note that it has the ability to dissolve in water, but it can't carry an electric current. So notice that sugar, the yellow sugar globs are like dispersed in the liquid, but you notice that there's no carrying of a current. So sugar dissolves completely, but there's no ions. And that is what they call a non-electrolyte. Because an electrolyte forms ions, so sugar and other covalent molecules are called non-electrolytes. And then this last one. So this last one, it's acetic acid. Yep, that one's a non-electrolyte. But this last example over on the far right shows molecules where, do you see that there's only a few ions that are formed? So in that, there's 4 of the CH3COOH are already together, and only one actually split and formed an H plus and a CH3COO minus. Only one of them formed ions. So there are some salts that do not split into ions very much, just a little bit. So those became what they called weak electrolytes. So a weak electrolyte only forms a few ions. And I totally forgot to bring my light bulb apparatus. I have a light bulb apparatus. I'll bring it next time. I was sitting in my office. I was like, there's something else I had to do. Oh, well. Totally forgot. But I will bring it next time so that I can show you like a strong versus a weak versus a non-electrolyte. Bring examples of them as well. But if it only forms a little bit, it can only carry an electric current a little bit. So in this, they use a light bulb. See that kind of like glowing thing in the middle at the top? So they use a light bulb as a way of trying to measure whether it's an electrolyte. And that magnesium chloride, the light bulb's really bright. When you look at the non-electrolyte, you notice that the light bulb looks like there's nothing happening. And then this last one, see how it looks kind of reddish colored? So it's actually supposed to show it that it looks really dim. I don't know why it turns red, but so the idea is, you'll see next week when I do it, because or not next week, I'll bring it on Wednesday. So you'll be able to see how a strong electrolyte versus a weak electrolyte, when you put it on, connect it to the solution to a light bulb, the sodium chloride is like really bright, okay? Because it's 100% of ions. The sugar doesn't light up at all because there's no ions. But the vinegar, the CH3COOH, which is that last one, it is a weak electrolyte, and it'll light the light bulb up like dimly. So it'll have barely a glow. And that's because it doesn't make very many ions. Like 5% form ions, 95% don't. So you can actually write out like a reaction for a strong electrolyte. So when you go to write out the reaction for a strong electrolyte, you always put the salt on the left, the arrow with water, and then notice that it's a one direction, the arrow goes in one direction, and you split the metal into its positive charge, the non-metal into its negative charge. So it forms magnesium ions and chloride ions. And you do need to go back and balance, but can you see in this one magnesium on each side, 2 chlorines and MgCl2, so you have to put a 2 in front of the Cl minus to show that there's 2 of them. They didn't put in AQ. This should say AQ as well, because anything on that side should be aqueous. And if this is solid, it really should have an S. So right after, because it says right here, solid magnesium chloride dissolves in water to yield magnesium and chloride ions.
Where?
Yep, right at C right here. So that's the S. It's just a way of saying like that the reactant was a solid. I put it in water and it forms ions. And that has the ability to carry an electric current. But then look at the difference. So if it's a non-electrolyte, I take sugar, which is a solid, I put it into water, now it's sugar aqueous. But do you notice that the formula doesn't change? I think non-electrolytes are the easiest ones to write because whatever's on the reactant side goes on the product side. It just changes from solid to aqueous, which just means it's dissolved. So the only difference between the reactant and the product is the phase, solid versus AQ. It's always going to be balanced, so you don't have to worry about balancing it. And this is what happens with covalent polar molecules. They can mix with water, but they don't split up into ions. Now, if you have a weak electrolyte, notice the arrow. A weak electrolyte is going to have an arrow going both directions because remember we said that's a reversible reaction. So one, the arrow goes in both directions. So that shows that some reactant becomes product, but eventually some product becomes reactant. So in the beaker, I will end up with all of it. I will end up with reactant and product all together in the beaker after a while, when it reaches the point of equilibrium, when it reaches the point where it's balanced. But notice on this one, CH3COOH on the left is a liquid. CH3COO minus on the right is aqueous, and then that H plus is also. See here and here, there's the AQ.
What about the L?
The L means liquid because vinegar, that's what this is vinegar exists as a liquid initially. S is solid, L is liquid, G would be gas, but AQ, this is aqueous. So notice in these, the products are always aqueous. But this is the one that's the weak electrolyte because 95% of the molecules don't form ions. Only about 5% of the molecules do. So that's why it doesn't light a light bulb very much, just a little bit. Okay, so here's a couple to practice just to see if you can do the hydration. So the first one, in a strong electrolyte, and I would always tell you, you wouldn't have to just know, okay? So, and I wrote the steps going down the right side. So if you have a strong electrolyte like HCl, and there's an L, so that means it's a liquid. If I put it in water, if it's a strong electrolyte, then you separate the reactant into ions. So I take the H and the Cl are going to separate. So you know what will be the charge on the Cl? Chlorine always ends up with a negative. So the chlorine ends up with a negative, right? So the chlorine, because it's over in group 7, right, like sodium chloride, the chloride's always negative, and that's going to be AQ. So the H is going to end up with an H, and it's going to be a positive. You separate the first group and the second group, separate them out, add AQ to the product side, and then balance if you need to. This one, do you see one H and one H, one Cl and one Cl? So it's already balanced. Can you see that? So that there's the formula HCl means one hydrogen. Over on the product side, H plus, one hydrogen. So there's 1 and 1. Same thing with chlorine. Chlorine is 1 on the HCl side and 1 for the Cl minus. So it's already balanced, so I don't have to add anything. So remember, that would be like this is a 1, this is a 1, this is a 1. You would have 1 of each of them. But now, what about Fe2O3? If you put Fe2O3 in water and it's a strong electrolyte, it's going to split. And so what's one of the ions you'll get? So the oxygen. And you know the charge on oxygen is, it's in group 6, so the charge will be a minus 2. And then the other one is Fe. And now in this one, remember figuring out the charge on the Fe, because the oxygen's a minus 2, the Fe has 2 of them. So the number of oxygens tells you the charge on the iron. So that's a plus 3. And now the last thing, in balancing, what do I have to put in front of the Fe? If on the left it's Fe2O3, how many iron is that? So that means I got to put a 2 over on this side. Okay, so Fe2O3 on the left, I have 2 irons, so I have to put a 2 in front of the Fe on the right. What do I have to put in front of the oxygen on the right? Look at the formula on the left. How many oxygens? 3. So that means that I got to put what on the right? I got to put a 3. So that's going to balance them. 2 iron on both sides, 2 oxygen on both sides to balance them. Now, if I have a weak electrolyte, then I have the double arrow. That's different than the strong electrolyte. Strong electrolyte arrow goes left to right. Weak electrolyte's going to go both directions. I'm still going to separate them into ions. So this one, Na2CO3.
Was this F2O3, that was for the first steps, right? We still going with the first one. Is it the strong F?
So that's this.
Yeah.
Okay? So now we're going to the next one. So we're looking at weak electrolytes. So that's the steps for this. So in this one, you see the double arrow. Water is above. Separate Na2CO3. What would one of them be? Separate them into ions. So that is the carbonate, so CO3 with a 2 minus. And then how many NAs? So Na, what's its charge? What's the charge on sodium? It's in group 1. Sodium is always a plus. It's always a plus 1. And that would be AQ plus CO3, AQ. So notice all the product sides get the little AQ symbol. So I separated them into ions. I determined their charge. I add AQ to the end of at the end of Na, AQ at the end of CO3, 2 minus. Now, if I've got a balance, how many sodiums do I need on the right side? I have 2 sodiums in Na2CO3. How many CO3s do I need? No. So CO3, remember, is a polyatomic ion. So I have 1 of those on the left side. So how many will I have to have on the right? If I had 2, that would give me 2 carbons and 6 oxygens. Do you see that? That would double it. So if I have 1 CO3 in Na2CO3, so I look at this, and I only have 1 of them, then that means that I only need 1 on the product side. So the formula, you're going to use the formula of the salt to figure out the number of those ions. So because Na2CO3, I got to put a 2 in front of the sodium. But CO3 doesn't have any parentheses around it or anything, so I know it's just a single CO3. And that's a polyatomic, so that's one you'd have to like look up if you weren't sure what it was. Last one, so HF, hydrogen fluoride. So if I split this up, what will the H be? H with what charge? Positive 1. And then what will be the fluorine? A negative 1, because it's in group 7, right? So there I separated it into ions, determine the charge, put AQ after. AQ. And now, how many hydrogens will I need to put to balance it? The formula is HF. How many hydrogens in HF? There's 1. So that means that in front of the H plus, I just have a 1. Okay, the HF has how many fluorines? 1. So how many would I put in front? So that's a 1 and a 1. So it's kind of like HCl up at the very top. It's just hydrogen fluoride. It's not very soluble in water, so it doesn't dissociate or form ions 100%. So the last ones are called non-electrolytes, and these ones are the easiest. One, you have an arrow going from left to right. You have water above, which means it's dissolved in water. You don't have to figure out ions. You don't have to split up the reactant into ions or anything. You just list whatever is on the reactant side, you just list it on the product side. It just changes from whatever form it was in to aqueous, and that's it. It'll always be balanced. So this first one, ethanol, if you take ethanol and put it in water, shake it up, totally mixes. So what do I have to write on the opposite side? So it's going to be CH3, CH2, OH. I just write the reactant on the product side. What do I write afterwards?
L.
No, because it starts off as a liquid, but when you put it in water, it becomes aqueous. When you add water, notice all of these, the product side's all aqueous. And then do you notice it's already balanced? You don't have to worry about balancing a non-electrolyte because they don't separate into ions. They stay connected. So there's table sugar. Table sugar is C12H22O11. It's a solid. So if I take some sucrose or table sugar and I put it in water, stir it up, it dissolves. What happens to that sugar? What do I write on the product side?
H.
C12, 22O, 11. And what do I put at the end? So it starts off as a solid. So the things in parentheses are solids, liquids, gases, or aqueous. That's just telling you what the state of it is. Okay? But just know a non-electrolyte's always going to be balanced, so you don't have to try to figure out what it is. It's going to be a one-in-one because all of this is doing is just dissolving. It's going from being a solid or a liquid to being an aqueous form. Okay, so I'll bring my light bulb so that you can see it next time. In the body, ions exist dissolved as part of a solution. One term that you might see are what are called equivalents. So EQs, most of your lab tests that come back, they don't come back in grams or moles or any of those. They talk about EQs, equivalents or milli-equivalents, and then they're going to give you like a range. This is normal. So 10 to 20 milli-equivalents per liter is normal, and here's what your patient's number is. All that milli-equivalents is talking about is it is really giving you the amount based on its charge and the number of molecules. So do you remember a mole? 1 mole of anything is the gram formula mass. An equivalent is its mole value times the number of charges it has. So like sodium, an EQ in a mole, exactly the same because you see it has a +1 charge. But notice that calcium, there'd be 2 equivalents of calcium per mole because calcium has a +2 charge. So all equivalent is doing is referring to the amount of that ion times its charge. So like with sulfate, SO4 2-, 1 mole of sulfate is equal to 2 equivalents because the charge on the sulfate, that charge tells you the equivalent. Chlorine ion's a 1, -1. So notice it would just be a 1. They're equal, same thing with sodium. But calcium and sulfate, which have a +2 and a -2 respectively, you would have more equivalents because they have more of a charge. So just know that you'll see that. When you see milli-equivalent, don't let that throw you. It's really just talking about the concentration of a salt, of an ionic compound that's present in a solution. Okay, so this brings us into some of the math. So we're going to talk about concentration of mixtures. So when you think about concentration, it is always how much of the solute compared to the total amount of the solution. So this is one we did last week, like in the osmosis lab, if you were in lab, but we were measuring out salt and we were adding it to water to make a solution, remember? So this is going to be the same. There's a couple of different ways to do this. The first one is called molarity. So molarity, this big capital M, so if you have like 2.0 molar NaCl, that capital M is just talking about a solution. So you can just take that capital M and convert it to what it means. It means moles per 1 liter. So it's how much of your solute per 1 liter of its solution. So just take this M and change it. So it's telling you that I have 2 moles of NaCl per 1 liter of the solution. And this is really probably the hardest part. You can't like use mole, just like you can't use percent. We had to convert in lab last week, we had to convert percent into what it meant so we could use it in math. But capital M is just a short way of talking about a concentration. So it doesn't matter if it was 2.0 molar or if it was 15.86 molar or if it was 0.00034 molar, whatever that number is, take the capital M away, put moles divided by 1 liter of the solution. That's really what that capital M means. So to figure out how much of your substance that you have, it is concentration times volume. So concentration, and this is going to be moles per liter times volume in liters. So do you see in this, if I take the concentration times the volumes will cancel? Do you see that liters and liters will cancel? That's going to tell me how much my solute. So for example, in lab, we made soap, but we did it by mixing a fat or an oil with 40 milliliters of 6 molar NaOH. So the first question is, well, how many moles of sodium hydroxide is this? 6 molar NaOH. That's the concentration. So 1, figure out what your concentration is. Six capital M NaOH. And what is this going to mean? Take the M and convert it to what it means. It's going to equal 6 moles over 1 liter of solution. And then 2, determine the volume. What is the volume? How much of that 6 molar? 40 what? So I used 40 milliliters. Now, do you see if I tried to multiply those, milliliters and liters don't cancel? So I'm going to have to take milliliters and convert it to, I got to convert it to liter. Okay, so if I'm using molarity and I have a volume in milliliters, I need to do a single unit conversion and convert it to liters. So in this, 40 ml times in a line, it's just a single unit conversion. What unit goes on the bottom? Milliliters. And the unit you want is liters. Anytime you see milli gets what? 1,000. So milli gets 1,000, liters gets a 1. So if you take 40 divided by 1,000, anybody need a calculator? I brought some. 40 divided by 1,000.
I don't need one.
Then that's 0.04. That one. Okay. So now I have my concentration and volume. So the rule is to figure out how much of your solid concentration times volume. So you're going to take 6 moles NaOH per 1 liter times the volume of it, and the liter and liter will cancel, and it'll tell you how many moles. So concentration times volume. So 6 moles per 1 liter times 0.04 liters is equal to 0.2 0.24. Do you see that in that liters and liters cancel? So you're always going to figure out like, what does the concentration unit mean? Multiply it times the volume. So the second part of this, so this is like A, that's always concentration times volume. But the second part we actually did in chapter 3. So if I know it's 0.24 moles of NaOH, and I want to know how many grams that is. Do you remember how to do that? Going from moles to grams. You've got to use the periodic table, and you got to look up what? Look up the mass of sodium. So what's the mass of sodium? So it's 22.9898. On here, rounds to what? 23. So sodium is 23, and there's only one of them because it's NaOH. Then oxygen weighs? O. So round it to 16. And then the hydrogen weighs 1. Right, so 23 plus 16 plus 1 is, add these up, 40. So there's 40 grams in 1 mole. So remember, you got to use the periodic table. If you have grams and moles, you're going to need the periodic table because you're going to need to be able to look what the mass is, just round those masses to whole numbers. So if I know, I'll just put it up here, 0.24 moles of NaOH times in a line. What unit am I going to put on the bottom? There. So moles goes on the bottom, and grams goes on the top. And how many grams in 1 mole? 40. So then you just do the math. So 0.24 times 40. Yep, 9.6. 9.6 grams of NaOH. This one's kind of like 2 steps. Now, percent solutions are not as much because percent goes straight to grams. But if you have moles, and the reason they do this is because when talking about moles, we're talking about numbers of molecules. So in the first number, so I had 40 and 6. Yeah, I'd end up having to round because 6 moles is only 1 significant figure. 40 milliliters would be 1 significant figure, so I'd have to round that to 10. But I would tell you that I weighed out 9.6. So I don't usually round when I make a solution, but that would be fine. Yeah. Okay. Okay, so in this, take the capital M, convert it to moles per liter. Multiply it times the volume. Make sure that it's in liters for the volume. And then if you're asked how many grams, you need to figure out the formula mass. So you just add up the masses of each of the parts of the compound, 1 Na, 1 O, 1 H. That's how many grams is in 1 mole. Okay, so here's another one. So 88 grams of sodium chloride is mixed in water to make a final volume of 0.75 liters. What is the molar concentration? So this one's kind of going backwards, right? So what I want to know molar concentration. I want to know what is big M, right? So if I want to know the molar concentration, I want to know, I've got to put moles divided by liters of the solution. Right, so that's what big M means. Capital M means moles per liters of solution. So I've got to figure out how many moles, and then I got to figure out the volume in liters, and I just divide them. So I know 88 grams. 88 grams of NaCl. I need to know how many moles is this. So you look at sodium chloride. Sodium weighs 23. Looking at the periodic table. The mass of sodium, 23. The mass of chlorine is? So it's like 35.45, so we just round down. So it's 35. I got to add those. So this is 8 and this is 5. Squinting. Okay, so if I want to convert this, 88 grams NaCl times in a line, what unit goes on the bottom? Grams. Right? Moles goes on the top. So the first thing I'm doing is I'm figuring out how many moles is that. Grams gets the what?
The 58.
Moles gets the 1. Moles always gets the 1 when you're doing a conversion. So then 88 divided by 58 is 1.517241379 moles. Did you get that?
Yeah.
Yep. So it would be 1.5. I wouldn't round it till I got to the end because remember the end is the molar concentration. So I'll just keep that number. So now I know moles, and now I have to divide it by the volume. So the first thing I had to do here, I had to convert grams to moles. And then I'm going to take that mole number and divide it by the volume of my solution. So what's the volume of my solution?
58.
Nope.
What you got?
Read the question. What is the volume of my solution? 0.75. So that number, 1.5172, all that, divided by 0.75. I got 2.022988506, and that's going to be my moles per liter, capital M. And so now, that's my answer, right? Because I wanted to know the molar concentration. So what would I round that to?
How many significants?
How many? 88 has
2.
0.75 has 2. So that means that my answer should have,
0.02.
I should only have 2. So it would be 2.0 molar NaCl. Right? The first 2 that you come to. So if you're given the mass of a solute and the volume, this is how you figure out the concentration. If you're given the concentration in the volume, you can figure out the mass of your solute. They're kind of going backwards. Do you see that? This one's going from grams to molar mass, or to molar concentration. This one that I did here is going from molar concentration and figuring out the grams. So they're exactly the opposite. But in both cases, you need to know the formula mass, because if you have grams and moles, you're going to have to know the formula mass, that 58 grams is in 1 mole for sodium chloride in order to solve. So here's another one. How many grams of glucose is in a 3.0 liter solution with a concentration of 0.65 capital M glucose, which is molar? So what does this number mean? When you see that capital M, just convert it to what it means. This means what?
0.65
What does capital M mean? Moles. Over.
liter.
That's what that capital M means, moles per liter. You can think of moles per 1 liter if it helps to give yourself a number down there, or just moles per liter. Just take that capital M and make sure that you convert it to what it means. Because remember in lab we were saying like percent, you can't use a percent. You've got to convert it to what does percent mean? Grams per 100 mils, okay? Same thing with molar. You've got to convert it. And I'll actually give you the formula mass for glucose in this one, so you don't even have to figure it out. So if I know the concentration and I know the volume. The concentration is 0.65 moles of glucose per liter. The volume is what?
180.
Nope, 180, that's how many grams is in 1 mole. That's how many, that's the molar mass. that 3.0 liters. Okay, so 0.65 moles per liter. That's the concentration. 3.0 liters, that is the volume. So what do I have to do to figure out moles?
Okay. So you
Hmm?
wanna
What do I have to do with these two numbers? Do I multiply, divide, add, subtract? Multiply, because what will happen to your liters? They'll cancel. Do you see that liters and liters will cancel? Concentration times volume tells you the amount of solute. So 0.65 times 3 is 1.95. Okay, so that's kind of like a step you want to remember. Concentration times volume equals the amount of your solute. You just have to make sure that the volumes are in the same units. You cannot multiply milliliters and liters. You got to make sure they're both in liters or both in milliliters. As long as they're in the same unit, then I know that those volume amounts will cancel and it'll tell me how much of my solute that I have. So now I know that I have 1.95 moles of glucose. But what I want to know grams. So I know moles, 1.95 moles of glucose. How do I convert that to grams? What do I put on the bottom? What do I put on the top? No, I'm going from grams. And what's the number in front of grams? 180. Yep, I gave you. So I said the formula mass of glucose. So this way you didn't even have to figure it out. So I didn't give you the formula for glucose. I just referred to it as a name. So if I give it to you as a name, like if I said like TNT, trinitrotoluene, I'd have to either give you the formula or I'd have to tell you what the formula mass is. Okay? So notice moles and moles are going to cancel here. So 1.95 times 180. 1.95 times 180 ends up being 1.95 times 180 moles and moles will cancel and it's going to tell you your answer in grams. I got 351. Can I keep that?
Well, you got three significant figures.
How many up above though? Two. So that means I can keep the 3 and the 5, but the 1 is going to do what? Drop. So this would be just 350. Okay, so that's two significant figures in that answer. So concentration times volume tells you the amount of your solute. If your concentration is in moles, you have to multiply times the formula mass to figure out how many grams of solute. So if amount of solute is in moles, because you use that capital M, then you're just going to multiply the moles of solute times the formula mass. Does that make sense? So this is sort of like a two-step. First step is always going to be this. Concentration times volume will tell you how much of your solute. But if the amount of solute is in moles, you're going to have to multiply it times the formula mass. That'll convert from moles to grams. And that's going to tell you grams of solute. So it is kind of like an extra step if you use moles. Got it? So that's kind of the second. So 2. Step 1, concentration times volume, tells you how much of your solute. Step 2, if the amount of your solute is in moles, multiply the mass, the number of moles of the solute times that formula mass, and that'll convert your answer to grams. And then number 3 is always significant figures, right? All right. So, what about this? No, not this one. Let's just go on to percent. Because percent takes out the whole grams to moles thing. Because percent is what we did in lab last week. Remember, you made a, 1.3% solution of sodium chloride. You made a 15% solution of sodium chloride. So when you see percent, you are always going to change percent to what it means. Okay? If you are talking about a solute that's a solid and a solution that is a liquid, like our mixtures, what we've been talking about, how you have things dissolved in water, then its percent stands for grams per 100 mils of solution. So if you see this, 5% sodium chloride, change the percent to 5 grams divided by 100 mils solution. So in this one, 12.5% sodium chloride means that there's 12.5 grams of sodium chloride per every 100 mils of solution. And I'm going to do the exact same thing. Concentration times volume tells me the amount of solute. So I'm going to use that exact same step, but it's going to give me my answer in grams in one step. I don't have to work with moles. That's molarity. If I have percents, so it says you need to make a 23% glucose solution to feed your newborn snakes. If the final volume of the glucose solutions needs to be 200 with the decimal place exactly, how much glucose will you need? So I want to know how much glucose. I want to know glucose in grams, right? When I want to know how much glucose, I know that I need to find grams of glucose. Concentration times volume equals grams of your solute. So what's my concentration?
200.
Nope. I know concentration. Concentration is 23.0% glucose. So see that at the top? If you see a percent, then you know it's a percent solution. So now I want you to change, what does the percent mean?
Over 100.
Okay, so it's 23.0 over 100. What do I have to put after the 23.0? Huh? Grams. Right? So that's what I said in this. If you have percent, drop the percent and put grams over 100 mils. So here, 23.0%, drop the percent and put G over 100 mils. So this, all percent, change it to that. Just like molar, change it to moles per moles per liter. This, you're going to change it to grams per 100 mils. So concentration times volume is going to tell me how much glucose. So where's my volume?
It's going to be down at the bottom over there.
In the problem, what is my volume? Concentration times volume, 200 milliliters. I'm going to take 23.0 times 200 divided by 100. Multiply everything across the top. So the best plan to do with this, so that you don't, should be 46 grams. Yes? 23.0 times 200 divided by 100. Should get 46 grams. Now, in this, 23.0, so this is grams of glucose. So this is my answer, right? So in this, 23.0, how many significant figures? How many significant figures in that number?
2.
Nope.
3.
Yep, 23.0, 0 with the decimal place, that's 3 significant figures. 200 with the decimal place has
3.
3. So that means that my number needs to have 3. It only has 2. So what am I going to have to add?
A 0.
Yep, 46.0 grams of glucose. So it's really telling you to be very exact.
So you gonna count us on? We ain't got this.
Well, that's always the last thing to do is check your significant figures, right? It's always the last. And that'll literally be like the last question will be like, apply significant figure rules and give me the right answer. Okay?
But on our test.
On your test, it will say, apply significant figures and give me the right answer. So you find the answer, and then you got to always go back to the numbers in the problem.
What I'm asking
right?
is, if we miss our 0.
Yeah, minus 1.
-1, we done got to the whole problem.
Yep. Well, the whole problem itself is usually worth 7 or 8 points. So if you don't get significant figures at the end, then I take off partial credit. Okay? All right, so let's look at this one. So you want to make a 12% sodium chloride solution to add to your fish tank, and you need a total volume of 625 mils. How much sodium chloride do you need to weigh out? So what I want to know grams of sodium chloride, right? Because when you weigh something, it's in grams. So this means I want to find grams of sodium chloride. And what do I know?
It's 12.
12%. What is 12% NaCl? What does that mean? 12 grams over 100 milliliters. So do you see that? So the G divided by 100 ml, that's the percent sign. Just like capital M becomes moles per liter, percent becomes grams per 100 mil. And then, what do I have to do? Times 625. Because then milliliters and milliliters will cancel. 12 times 625, then divided by 100. Yep, 75 grams of sodium chloride.
But we got
Do I need to round?
add a 0.
Do I need to round?
Now you got to
Look,
round and
look at the top. Look at the numbers at the top. 12% has how many significant figures? 2. 625 has 3. So that means my answer should only have 2. So am I good?
No, you gonna round it to 80.
No, 75 is 2. Remember, 80 would only be 1. I don't. This one I don't have to. Sometimes you don't have to round it, but you always look back at the measured numbers.
Because it's 5, you gotta go with 1.
No, you don't. Right? Yeah.
I don't want to know why you round.
You don't have to round this.
I'm rounding to 5, right?
But then that would make 80, and 80 would only have 1 significant figure. Right? 75 has 2 significant figures, so I don't have to do anything to this number. The 7 and the 5, those are my 2 significant figures in my answer. And 12% has 2 significant figures, so I'm good. You always take the lowest number of significant figures in the problem. Okay? Where's the what? Oh, that's 2 significant figures in 12%, 3 significant figures in 625. All right, here's the tricky question. How much water do you need? What did you do in lab? You had to make a 15% solution of sodium chloride. So you had to go weigh out your sodium chloride, and you had it in a little dish, and then what did you do with it? The graduated cylinder, right? You dumped it into the graduated cylinder. So you had this white crystal down in the bottom. And then you added, you filled it all the way up to the 100, right? Remember, you filled it all the way up to the 100. I made up one that was 250, but you guys just had the little ones. Okay, we don't give you the big cylinders because they cost a lot and you might break them. But you get the little graduated cylinder. So you put white powder, you put the salt solution, the salt crystals in that graduated cylinder, and then you added water to the mark. Do you know exactly how much water you added? No, you were over there at the distilled water box, right? You were like, hopefully you didn't go over. I had some people that like went up past the 100, and I was like, you have to stop. You have to start over. And they're like, right? So do you really know how much water you added? No. You have to add enough to make the total volume. What? What is my total volume? I would go weigh out 75 grams of sodium chloride, put it into a container, and add enough water to make the total volume 625 mils. So here's a note. You don't know
Jesus Christ.
the exact amount
So, what
of water,
is that? We don't know it.
right? You don't know the exact, like, have you ever
So
made
we
like
can get that
lemonade?
wrong, but we don't-
Have you ever made lemonade? Okay, like lemonade from a crystal, like country time lemonade, right? So you put a couple scoops of the lemonade and you just add water, and it says makes 2 quarts. That is the entire solution, is 2 quarts. That doesn't mean it has 2 quarts of water in it. It has 2 quarts of lemon crystals and water together, because that is the total volume of the solution, not just the water. So that's why I say when you make up solutions, you usually don't know exactly how much water. That's why you had to put your crystals in the graduated cylinder first. Because I had one student that went over and she was like, okay, I filled it up to the 100. And I was like, well, what's going to happen when you add your salt? She was like, it'll go over 100. And I was like, exactly. Make sure you dump out at least 15 mils of water. Make sure you leave space, because some of that volume will be the salt, or in this case, it's a salt. Some of it will be the sodium chloride that dissolves into the water, but it still is going to take up some space. Does that make sense? Okay. So when you think of 100 mils, that's not 100 mils of water. That's 100 mils of solution. So when we talk about this, so that grams per 100 mils, that's not grams per 100 mils of water. That is grams per 100 mils of solution, which is solvent and solute. Right? It's the sugar and the water, the salt and the water mixed together. All right. Does that make sense then? Okay. But I think percent solutions are way easier, because you don't have to mess with molar mass and all of those. But you use molar concentrations when you're talking about a chemical reaction, because chemical reaction is related to numbers of molecules. So that's why you have to use moles. So in this, physiological saline is 0.90% sodium chloride. So how would you make up 500 milliliters of physiological saline? So what is my, and so do you notice this? I have percent. Percent is concentration, and I know volume. Concentration times volume is going to tell me how much of my solute I need. So what is 0.90% change to? Yes, divided by 100 mils. So has everybody got that? That's what percent means. So when you have percent, change it to grams over 100 mils. And remember, that's 100 mils of the solution. Now I've got to multiply it times 500 mils. Concentration times volume. Do you see milliliters and milliliters are the same? If that was 0.5 liters, I'd have to convert it to milliliters. You've got to have the volumes the same. With percent, both volumes need to be in milliliters. I can't have milliliters in liters. Does that make sense? You've got to make sure that these can cancel. The only way that those volume amounts will cancel is if they're the same. So 0.090 times 500 is? Is 4.5? 0.45, sorry. 0.45 grams of NaCl. What's the last thing to do? Significant figures. Okay, so 0.90% is how many significant figures? 2. Because remember, those zeros out front don't count.
We're going to leave it just like it is.
What about 500?
3, but we're going with
It
the
only has 1. 5. No decimal place, those zeros, so it's just 1. So that would have to be what? So do you see why? So in that previous one that we had, like up here, 23.03 significant figures, 200 with a decimal place, 3 significant figures. That's why I had to add that 46.0. I had to make sure my answer was 3 significant figures. This one, though, it just says 500. So it might be 499 or 501, so I don't know the exact, so that's why I have to round it. Okay? All right, I'm going to stop there. Okay. The last thing that we have to do in concentration is parts per million and parts per billion, which again, really pretty straightforward because it's just grams and mils. Okay. It's just talking about really, really small amounts. So sit down and kind of write out how you figure out molarity. How do you figure out concentration from percent? Because getting those two straight, when you get them on your take home test, you'll be like, I got this. You won't be like, I don't know what to do. Write down next Monday. Next Monday, I'll give it out. Part of the questions, more like theory, multiple choice kinds of questions, are in Moodle. But then stuff like this, you're going to have to write it out. Part of it's going to be paper and part of it will be questions in Moodle. The ones that I do in Moodle is just so that I can grade them quickly. But they're multiple choice questions. Okay? But questions that involve math, I'm going to give you on paper so that you can write it out. Because if you write it out and make a mistake, but you get almost all of it, then you're going to get partial credit. If you just leave stuff blank, then it ends up really hurting your grade. So that's why I'm you want to sit down and try to write out the steps for solving molarity questions, percent solution questions, and then we'll do parts per million, parts per billion, and dilutions next time. Okay? Whew.